remaining oxygen is making water with 2 hydrogen ions, right? And because this is existing as solid, so we will write this as solid, okay? Though in ionic equation, writing solid looks a little weird to me, but yeah, this is in the solid state because this is insoluble, okay? And I did not write copper, though it is in the solid state, but it has an oxidation state of 2+. I did not cancel it, you know. I can write, you know, you can write copper 2+ and then, you know, copper 2+ here as well, but then again you will see the same ion on both the sides, so I did not write it, okay? And that's how they have given this equation in your book as well. Okay, so this is how they came up with this. Okay, any questions regarding this equation? Yes, Maruch, copper chloride formula, by the way, is wrong. Where did carbonate come from? What do you mean, Yusra? Carbonate, copper carbonate was one of the reactants they gave us in the question, right? Yes, that's where we got the carbonate. Okay, let's move on. Carbonate is here, see? Question number 4, copper carbonate. Carbonate, okay. Let's move on to the end of chapter questions. Okay, do you guys want to do this worksheet first that your teacher gave today? Yeah, I only wrote, no, you don't want to do. Why is carbonate solid? Because it is in the, it is insoluble. It is in the solid state. It is in the solid state. That is why copper carbonate is in the solid state. That's why I wrote solid. I did not write copper. I did not write copper because it is on both the sides of the equation. It won't make sense if I write copper. Well, you can. I mean, it's in the solid state, and here it's in the aqueous state. So yeah, state is different. You know, state is different. Here it is in the solid state held. Here it is in the aqueous state. That's the only difference. Okay, you can write, you know, but you will have to write it like this. Solid, okay, and here aqueous, showing that it has dissolved. That's all, nothing else. Okay, if that's confusing you, you can write it this way. Okay, I think if you write this way, it should be correct, if you ask me, but I don't know. Okay, so you want to do end of chapter questions or you want to do this worksheet? The worksheet is easy, Hiba. You want to do difficult things, right? With me. Okay. I was thinking of both. Okay, let's see. End of chapter questions. Hiba, what about the end of chapter questions? You find them easy or difficult? Easy. Okay. Who is this easy? The easy one will be answering the questions because it's easy, right? Okay, a group of students. Yusra, it's okay. If you don't have the worksheet, I will share with you. Don't worry. Yeah, the girls got a few sections of the girls wing, I think, got. Okay. Question number 1. I like this worksheet because it had a lot of oxidation state questions. So I thought maybe we can practice oxidation state from the worksheet, but that's fine. Let's do these questions first. You guys also got, Nabil? Okay. Okay, let's do these questions first. Okay, a group of students is conducting an experiment investigating the action of heat on solid copper carbonate, and zinc carbonate. Okay, the 2 experiments gave them the results summarized here. Now, copper carbonate is a green colored powder, okay, and they are only heating it. Both of them are carbonates. By the way, what do we know about carbonates? They are insoluble except for the first two groups and the ammonium carbonate. So what is this? Copper and zinc, both of them are transition. That means both of them are insoluble. Okay, keeping that in mind. Heat. Okay. Positive test for carbon dioxide gas given off. Remember, whenever you have carbonate and you heat it, you will get carbon dioxide. This is thermal decomposition. Okay, it will decompose into carbon dioxide. Positive test for carbon dioxide gas given off. Okay, then black powder. Cool down, again black powder. Okay, what do you think? Let's write down the equation here. You know, writing down the equation will make things easier for you. So copper carbonate, this is 2 minus 2 plus, okay, undergoing heat, giving us carbon dioxide. Okay, what is left behind? What is left behind? Carbon dioxide, CO2. What is left behind? Copper carbonate, Yusra? Yes, copper oxide. Copper oxide, okay. Now, you should also know the colors of a few compounds, okay? By solving a lot of questions, you will learn a few colors, okay? So this is copper oxide, and this is solid, black powder. This is black in color. So you should know. Solving a lot of questions will make you memorize a lot of things. Formulae, colors, you know, oxidation states, solubilities, all these things. The more questions you will solve, the more of this stuff you will remember. Okay, this is one. What is the other one? Zinc carbonate. And we are heating it, and positive test for carbon dioxide because it's a carbonate, so breaking down into carbon dioxide plus what else? If you take out carbon dioxide out of this, see, Yusra, try to imagine, try to visualize. I don't remember the exact oxide. Okay, this is for your visualization so that it's easy for you to understand. Then you're asking me, where did the carbonate go? This was carbonate, for example. I don't know if it looks like this. I just came up with this. Okay, CO2, and then what you're left behind with is zinc oxide. So zinc oxide. This is solid. Most of the oxides are solid at room temperature. Now this is a yellow powder. Yellow powder, but it turned white when we cooled it down. Okay, now what are the questions they are asking? What evidence is there that a chemical reaction has taken place in both the cases? Okay, tell me. Remember those 4 points I gave you, the 4 evidences of chemical reactions? First of all, you will get a new substance. You will get new chemicals, new products, new substances which will be completely different from the reactant. Okay, they will have completely different physical and chemical properties. That is number 1. Second, if you see a change in color, and you saw the change in color, okay, the color was black. If you see gas coming out, bubbles, carbon dioxide, all these are evidences that chemical reaction has taken place. Same is the case here. You saw a change in color, yellow powder, gas coming out, okay, and you got products which are completely different from the substance that you started with. So if there is a change, that means chemical reaction has taken place, okay? So these are evidences. I have discussed this, you know, when I was beginning this chapter. Okay, the evidences of chemical change. What is the major and most reliable evidence of a reaction here? Of all the carbon dioxide given off is the most reliable? Are you sure? I remember writing it somewhere down here. When I started taking classes, I wrote down the 4 signs of chemical changes. I don't know where did they go. I can't find, but I remember writing it down. Okay, I cannot find it. Okay, leave it. Okay, so the most reliable evidence, remember, of a chemical change is that the product which are formed are different from the reactant in their physical and chemical properties. I did not get time to check on the answers at the back. Are you guys checking my answers from the back? What is this? This is 4, right? Chapter 4. 4. Oh, there are no answers at the back. Oh, only in CD. Oh, okay. So if you have answers, then you can check. Okay. Does anybody have? Okay, I don't have the CD. Okay, what is the major and most reliable evidence of a reaction here? I think the most reliable evidence of any reaction is that a product is formed which has completely different physical and chemical properties from the reactant that you started with. Most reliable evidence is color change. Many color changes are not necessarily, I'm saying not necessarily, mostly they are, but you know, they are asking most reliable. So of all the evidences, which is the most reliable? I think it should be, you know, that that the products that you have ended up with are different from the reactant in their physical and chemical properties. And second number is the production of gas. Okay, second number is production of gas. Write word equations for the 2 reactions. That is easy. I don't think we need to do that. Copper. Okay, how will you write this? How will you write this? This formula. Will you just write copper carbonate, just simply like that? Copper carbonate. Will you just write like that? No. This is a transition metal, right? Yeah, this is a transition metal, right? Now, for example, if you have 2 girls with the same name in a class, or 2 boys with the same name in a class, for example, there are 2 Muhammads, okay, or there are 2 Ahmads, right? So what do? We take them, or we specify them by their last names as well. Muhammad Abu Bakr, ya Muhammad, jo bhi uska pura naam hai, right? Why do we do that? Because in order to differentiate that, okay, we're talking about this Muhammad. We have 2 Muhammad. I'm talking about this Muhammad. Or like, for example, if there are 2 Maryams, Maryam Ayaz or Maryam Tariq, whatever the name is, then you have to mention by the last name in order to specify, differentiate it. Which Maryam are you talking about? So same is the case with transition metals. Because we have copper +1 and we have copper 2+. So if you just write copper carbonate, people will say, which copper are you talking about? This or this? So remember, whenever the metal is transition, you have to mention in the brackets the oxidation state. Copper 2 carbonate. I'm talking about copper 2, okay? Now zinc. Zinc is also transition. Zinc is also transition. I'm not sure if it has any other oxidation state other than, but most of the transition metals have more than 1 oxidation states. That is one of the properties of transition metals. I cannot remember any, but if it has more than 1 oxidation states, then you will mention zinc 2 carbonate. But I don't remember seeing it this way, written this way. But if it is, then you know this is how you will write. Then zinc carbonate, and then this is easy: carbon dioxide, copper oxide, carbon dioxide, and zinc oxide, and so on and so forth. Okay, another thing while writing formulae, which is very important when you are calculating oxidation states, remember whether a molecule is covalent, ionic, whatever. When you write the formula, the the element that you write first, in the formula will always have positive oxidation state. Whatever oxidation state, but it will be positive if the element is written at the beginning of the formula. The element which is written at the end of the formula, or which is written later, will have oxidation state in negative. It can never be the other way around. You cannot have negative oxidation state first and positive oxidation state later. Yeah, Amna, I'm not using the word cation, anion, because in covalent molecules, we don't have cations and anions. So I'm only speaking in terms of oxidation states being positive and negative. And what does this mean, oxidation state being positive and negative? Meaning that the element which is more electronegative is written afterwards. The element which is less electronegative, or in other words, you can say that the element which is electropositive is written first in the formula. That is a universal rule. That is a universal rule. For example, let me give you an example. I'm sure you have not come across this before. This is not in ordinary chemistry, your O levels, but I'm just giving you an example to make this point clearer. For example, this formula. Now you are used to seeing hydrogen at the beginning of the formulas, right? H2O, HCl, H2SO4. I don't think you have ever come across a formula in which the H is written afterwards. Where the H is written at the end, right? Yes, HNO3, yes. But this compound also exists. And what do you think is the oxidation state of hydrogen here? No, I'm not talking about hydroxide, Hala. No, Dalal, I'm not talking about hydroxide. Hydroxide is different. That's a polyatomic ion, like on its own. I'm talking about hydrogen on its own, okay? Not as in the form of a polyatomic ion. That way you even have ammonium, okay? I'm talking about hydrogen on its own. Here, the oxidation state of hydrogen would be -1. Why -1? How -1? Because sodium is more electropositive. More electropositive compared to hydrogen. Now, hydrogen is a pretty electropositive element, but sodium is more electropositive than hydrogen. So when you are writing two elements together in the formula, you talk in terms of their relative electronegativity, or relative compared to each other. So sodium is more electropositive. So you talk about their electronegativity and electropositivity. Okay, electronegativity means like affinity for electron. So compared to sodium, hydrogen has a greater affinity for electron. So this was very important for writing oxidation states. Let's move on. Write a brief description of what you would see if zinc oxide powder were heated strongly and then allowed to cool down. Now, zinc oxide, when it was heated, when zinc carbonate was heated, we immediately had yellow powder. That was zinc oxide, by the way. And when we cooled it down, it turned into white, and it was still zinc oxide. Zinc oxide changes its color in response to change in temperature. When it's real hot, the color becomes yellow. It's called thermochromic. Thermo has to do with thermal energy. Chromic, color. It changes color with thermal energy. Okay, so I don't know with temperature there are changes in molecules, and that leads to different wavelengths being reflected. Okay, color has to do with the wavelengths that are being reflected, right? So we are not going into those details, but yes, remember that it is a solid that changes color in response to changes in temperature. Okay, so write a brief description of what you would see happen if zinc oxide powder were heated strongly. If you will heat it strongly, it will turn its color yellow back again, and then allowed to cool down. Allowed to cool down back to white. Okay, it can move from yellow to white, white to yellow, yellow to white, white to yellow. It can keep doing that. Okay, would this change have been a chemical reaction? Yeah, this is a tricky question. This is a tricky question. Now, we have studied that chemical change is only when a new substance is formed, right? But I would say that if there is a slight change in the molecule structure, even if there is a slight change in the structure of the molecule, that should also be regarded as a chemical change, because you changed the structure. You changed the structure, right? It is mentioned somewhere here. Here, this silver chloride, silver bromide and silver iodide behave in the, no. Silver chloride, a white solid, turns gray in sunlight because silver metal is formed. Silver bromide are the silver. No, this is chemical. I think it is a reversible chemical reaction. I think because there has been a change in the molecule. You can confirm with the CD. Maybe it is a physical change, but if I'm not wrong, I think there has been a change in the structure of the molecule, so that would be a reversible chemical change. Remember, chemical changes are also reversible, right? So will that make them physical change? I don't think so. So if there has been a change in the molecular structure, I would still call it a chemical change, but it is reversible. This is what I think. I am not sure though. Anyway, okay, let's move on. Redox means reduction and oxidation. It can be defined by loss and gain of oxygen or by loss and gain of electrons. Which definition is more useful? I think we have done this. We have done this, haven't we? Yeah, yes. Amna, your combustion question. Okay, what I found out about your combustion question was that you said your question, by the way, let me repeat your question for the rest of the students. You asked me that even if the oxygen supply is less, why don't the carbons combine with both the oxygens, and rather than making carbon monoxide, why don't they make carbon dioxide? I don't know if what I found out is absolutely correct or not, but what I think is that if you want the second oxygen atom to sit on your carbon, on the same carbon, okay, carbon monoxide, for example, this, if you want the other oxygen atom to also come and sit on it, you have to increase the concentration of oxygen, and you also have to allow for more time given to both the elements to react with each other. They should have more time, more exposure. Yeah, more exposure, more energy. They will require more energy. You can look at it this way. Yeah, you can look at it this way, that, you know, oxygen is pretty electronegative. Okay, we all know that. Oxygen and oxygen will repel each other. Okay, they will repel each other. They would not want to be sitting on the same carbon. It would be better to go and sit on a new carbon atom. Okay, so they will readily do that. Okay, by the way, let me tell you, this was an interesting thing I noticed in electrons and atoms. What they do is, you see, have you ever seen children sitting in a bus van? When a van is empty, these are seats, right? These are your van seats. I'm looking at the van from the top. Okay, this is the door and children are entering into the bus. How will they sit? These are window seats. These are windows. How do you sit in your school vans? Have you noticed? Provided you guys don't know each other. There are no friends. Children are from different places. They don't know each other. They're strangers. How will they sit? Everybody will want the window seat. Everybody will want the window seat. Nobody wants to cram up, right? Yes, window seat. Everybody wants the window seat. Now, if there are more kids coming, they will sit next. If more coming, they will sit next. Okay, otherwise, I mean, provided they are not friends, they would not sit together. Everybody would prefer a window seat. atoms and electrons behave the same way. So if they have a lot of carbon atoms, or each oxygen will sit alone. They don't want to sit together. But when all the oxygen atoms have already occupied carbon and you're still supplying more oxygen, there's plenty of oxygen, then the other oxygens have no other option. This is just an analogy, okay? So that was the answer that I came up with, okay? Let's move on. Next question. Yes, so electron definition is more useful, okay? Gain and loss of electron, that is a more useful definition. Is it possible to have oxidation without reduction in a chemical reaction? No. Yes, good job. Yes, yes, yes. Like you cannot give if there is nobody to take from you, right? Who will you give from? You won't throw it in the air. You won't do that, right? If you want to give, there should be somebody to take from you. Okay, question number 3. Have we done question number 3? Have we done? No. Okay. When a strip of burning magnesium ribbon is lowered into a gas jar of carbon dioxide, the following reaction takes place. So magnesium is reacting with carbon dioxide, magnesium oxide, and carbon is being formed. Okay, what observation would show that carbon had been produced? Observation. Carbon, not carbon dioxide. Yes, Ajwa, good job. Black powder, good job. Black powder, or we can call it char, C-H-A-R. It's also called char, you know, simple carbon. Okay, yes, black powder. Okay, write a word equation for this reaction. Is there any transition here? No. No, so this is easy, okay? Magnesium reacting with carbon dioxide gas, giving magnesium oxide plus carbon. By the way, what will be the state symbols? Carbon, we all know. Carbon is solid, that's easy. Magnesium oxide. What do you think? Gas? Aqueous? Yusra. Okay, what about solubility? Solubility, magnesium is in second group, right? Magnesium is in second group. Maybe it is aqueous, I don't know. Let me see. Potassium salts, all are soluble. I don't think it is soluble. It's not a salt. It is solid, okay? Because it is an ionic compound. It is an ionic compound, and it is an ionic compound, and it is not a salt. So it will be, oh, where am I? It will be solid, okay? This should be solid, okay? Yes, right, okay. Which substances have been reduced in this reaction? Okay, we will do this. Magnesium plus carbon dioxide giving magnesium oxide plus carbon. Tell me the oxidation state of each one by one. Magnesium is 1 by 1, 0, Hiba, good job. Carbon dioxide. What is carbon here? Yes, +4. How? Let's do this. Okay, let's do this. Carbon dioxide, how? Because we don't otherwise get time. So these are the rules. These are the rules. Okay, I have also shared in the group. Now let's go through these rules. Okay, element by itself is always 0. Itself, always 0. Diatomic, metallic, big molecule, small molecule. If it is bonding to itself, it is 0. Group 1A, group 1A is the first group. We're talking about this. This is 1A. This is 1A. This is always +1. When I write, when the word always, meaning no exception. No exception to this. Okay? Carbon 2A is always +2. Halogens are usually -1. Why did I write usually? Is because not always. There are exceptions. Halogens are positive with oxygen. With oxygen, halogen will be positive. For example, For example, ClO. For example, ClO, Cl2O. Cl2O. So what is the oxidation state of chlorine here? What is the oxidation state of chlorine here? So let's do this, okay? Oxygen का क्या rule है? Yeah, usually is -2. The only exception is peroxide. Oxygen is -2 usually. If the only exception is H2O2, only in H2O2 it is -1. Otherwise it is -2. So oxygen would be -2. Then this is 2, and the net charge is 2. So what should I add here to have 0? I should have +2, right? Now +2 is divided in 2 atoms. So that means one chlorine has +1. So the oxidation state of chlorine is +1 here. Okay, so this is what I mean when I am explaining this rule, that halogens are usually -1, but they are positive with oxygen. So here, halogen, chlorine was +1 with oxygen. Okay. Then if it's a neutral compound, the sum of all the oxidation states should be 0. Okay, another rule that I want you to pay attention to is that when writing oxidation numbers, sign is always written before the number. When writing charge, sign is written after the number. What do I mean by that? Like if I want to write the oxidation state of this, I will write +2. But if I write it in the ionic form, I will write it magnesium 2+. This is representing the charge on it, and this is representing the oxidation state. What is the difference between oxidation state and charge? Remember, what was the definition of oxidation state? Who remembers? Tell me, what was the definition I told you for oxidation state? Who will tell me? Oxidation state, yes. Okay, you are close, Yusra. Number of electrons participating. Number of electrons participating in the, in the bond or in the compound. Okay, so 2 electrons can be gained, can be lost. If lost, plus; if gained, negative. Okay, let me move on. Okay, so, okay, this oxygen. Now, oxygen rule is usually -2. The only exception is peroxide. So this is not peroxide, carbon dioxide. I'm finding out the oxidation state of each. So this is -2, but there are 2 of them. So -2 multiplied by 2 is -4. Now this is a neutral molecule. So whatever the oxidation state of carbon is, if I add them to -4, you will get 0. Okay. So this must be +4. For both to add up to 0, you should have +4. Okay. So carbon oxidation state is +4 here. Okay. Oxygen is -2. This is +2. Okay. Magnesium, because 2A, magnesium is 2A, always +2 without any exception. Oxygen -2. Carbon element by itself 0. So what is getting oxidized here? Okay, magnesium is getting oxidized. 0 to +2. This is oxidation. Okay, from +4 to 0. This is reduction. Okay, oxygen, nothing is happening to the oxygen. It's -2, -2, both. So not getting reduced or oxidized. Okay, now what is the next question? Which substances have been reduced in this reaction? Reduced, carbon has been reduced. Which substance has been oxidized in this reaction? Magnesium. Okay, okay. Let's move on. Magnesium oxide reacts with hydrochloric acid to make the salt magnesium chloride and water. Write the symbol equation for this reaction. Magnesium oxide. So is this difficult? Magnesium oxide reacts with hydrochloric acid to make the salt magnesium chloride and water. Magnesium sulfate is produced when magnesium is added to zinc sulfate solution. Write an ionic equation for this reaction. Okay, let's do this real quick. We are running out of time and we haven't even finished the end of chapter questions. And okay, magnesium oxide, I told you it is a solid, okay, will react with hydrochloric acid. So I know this is aqueous to make salt magnesium chloride. Magnesium chloride. Okay. You know how to write the formula, right? The oxidation state is +2. So I will write +2. I will write 2 here as a subscript next to chlorine. And water. All the chlorides are soluble except for lead and silver. This is not lead or silver, so this must be soluble. So this is aqueous. And this is liquid. Okay. Now I told you, okay. So that's it. Write the symbol equation for this reaction. Next question. Magnesium sulfate is produced when magnesium is added to zinc sulfate. When magnesium is added to zinc sulfate. This is solid. I know this is a metal. Zinc sulfate. All the sulfates are soluble except for barium, calcium, and lead. This is not barium, calcium, and lead, so this must be aqueous, giving us magnesium sulfate. So magnesium is displacing zinc because magnesium is more reactive. So magnesium sulfate, and so zinc is kicked out. So this is what? Displacement reaction, single displacement reaction. Write an ionic equation for this reaction. This is aqueous, this is solid. Okay, let's break them down into their respective ions, right? This is aqueous, so zinc plus sulfate ions. Okay, let me first find out what has happened. Okay, let's find out what has been oxidized and what has been reduced. This is 0. Okay, this is +2. This is +2. Okay, this is 0. Sulfate is the same. Nothing happened to sulfate. Okay, this got oxidized. This is oxidation. So let me write down the oxidation reduction, oxidation reaction. Oxidation is magnesium plus loss of 2 electrons, right? It lost 2 electrons. That's why it got 2+ charge. Zinc got reduced. Zinc got reduced. It must have gained electrons. +2 electrons into zinc solid. Right. Sulfate is unchanged on both sides of the equation, so it's just a spectator ion. Okay, we will not consider sulfate. 2 electrons, 2 electrons. Okay, now overall reaction will be, I always run out of space. Overall reaction would be magnesium solid and zinc 2+ on the left side, right? Magnesium solid plus zinc on the left side, and magnesium, this is aqueous. From magnesium sulfate, it was soluble. So magnesium aqueous plus zinc solid. Okay, right. This is the ionic equation. Zoom out. Yeah, this is the ionic equation. So Yes, the shortcut that I have told you most of the times works, but if you get something like this where you have solids on both sides, metals and metals, then you have to do it the proper way. Find out the oxidation, what is getting oxidized, write that half reaction. Find out what is being reduced. This is the reduction half reaction. Why are they called half reaction? Because they are half of the story of what's going on, right? So this is reduction, and the number of electrons, by the way, in both should be the same. Why? Because electrons, whatever it is giving, that is what it is accepting. So, I mean, you cannot have magnesium giving 2 electrons and this accepting only 1, or this giving 1 and this accepting 2. Both numbers have to be equal. If they are not equal, you have to balance the equations to get the number of electrons same. Because whatever the reducing agent, whatever the oxidizing agent is giving, the reducing agent should be accepting that many, right? Yes, so the last equation is the ionic equation. Yes, this one. This is the ionic equation. Okay, and you should know how we got it. By combining the oxidation and reduction reaction, find out what is getting oxidized, what is getting reduced. And if they ask you what are the spectator ions, sulfate is the spectator ion. Okay, okay. Okay, explain why magnesium is a reducing agent in this reaction. Yes, because very good, Hiba. Yes, Hiba. Magnesium itself is getting oxidized, and oxidized meaning it is losing electrons, because remember, oxidation is the loss of electrons. So as it is losing electron, it is giving away electrons. Those electrons are reducing zinc. So in this way, it is behaving as a reducing agent. Okay, I hope you understand this. I talked about oxidizing and reducing agent. Remember, I'm repeating myself. Whatever, for example, these are 2 atoms. Okay, this is giving away an electron to this. So this is getting oxidized. This is getting reduced. So because this is getting oxidized, but it is reducing this, right? So this is the reducing agent. Remember this diagram. And because this is accepting, therefore this is oxidizing. So this is the oxidizing agent. Okay, so remember this. Okay. We are out of time, but let me just okay, let's just do this question 4. Okay, I wouldn't feel good if I don't do. Okay, the equations A and B below show 2 reactions which lead to the formation of acid rain. Sulfur with oxygen sulfur dioxide, which then further reacts with oxygen trioxide to give sulfur trioxide and oxygen. Write a word equation for reaction A. Simple, yes, Yusra, yes. Sulfur plus oxygen giving sulfur dioxide. Good job. Which 2 of the following statements about reaction B are correct? Sulfur dioxide is oxidized to sulfur trioxide. Sulfur dioxide is reduced to sulfur trioxide. No. Now, one was, looking at the oxidation state. The other, I told you, was looking at the number of oxygen atoms as well. So simple, we can see that there are 2 oxygen atoms here and 3 oxygen atoms here. Okay, oxygen trioxide is reduced to oxygen, or oxygen trioxide is oxidized to oxygen. No, this is wrong. These 2 are absolutely wrong. Okay, but they look correct to me, but I have to verify. I will double check. How will I double check? Sulfur dioxide to sulfur trioxide. Now what's happening? This is -6, right? -2 multiplied by 3 is -6. So I should get +6 for total to be 0. So this is +6 here. If anybody is not understanding how I got this, please let me know. If anybody in this class is not getting what is this, what have I done this, then let me know. This is -4, right? -2. One oxygen atom is -2. So 2 oxygen atoms would be -2 multiplied by 2, which is -4. And if this is a neutral molecule, I should get +4 to get 0. So this should be +4. Huh. So yeah, this is oxidation. Can you see the oxidation state jumped up? This is oxidation. So not only can you decide that this is oxidation by looking at the number of oxygen atoms bonded in the molecule, but also can double check by looking at their oxidation states. And oxygen trioxide, now oxidation state, we cannot do this because they are by itself. I mean, they are bonded to themselves, so they will be 0 in both the cases. But yes, there is a reduction in the number of oxygen atoms. So in that way, looking that way, we can say that this is correct. So these two are correct, okay? Complete the equation to show how an aqueous solution of sulfuric acid is formed from sulfur trioxide. Let's try this out. Let's try this out. Sulfur trioxide plus something into H2SO4. Complete the equation to show how an aqueous solution of sulfuric acid is formed from sulfur trioxide. Okay, so we know that this SO3, so what is left? It's something like this. Oxygen is sulfur, okay. I don't know the exact, something like this. H2SO4 is something like this, okay? Now, SO3 meaning I am taking this out. What am I left with? This. This is what? H2O. Yes, H2O. Simple. Okay. Sulfur trioxide with water giving H2SO4. Okay, do you want to do more questions or is that it? Tell me. Or can we do question 5 real quick? No? More? I'm sorry I couldn't take questions from you today. That's it. Amna and Atika are tired. More. No, tired. Yusra is tired. More questions. Okay, let's just try this last. Okay, just try this last. Okay, just last and then you guys go. Okay, that's it. Okay, please. Oh. Okay, this last. Okay, which 3 of the following conduct electricity? Easy. Aqueous sodium chloride. Yes. Ceramics? No. Ceramic is an insulator. No. Copper is a metal. Yes. Graphite? Yes. Sodium chloride? Crystal. Crystal meaning this is ionic solid, meaning the charged particles are not mobile. So no. Sulfur, simple covalent molecule. No. Remember, for conduction, we need mobile charged particles. Mobile charged particles. Remember, state the name given to a substance such as plastic which does not conduct electricity. Insulators. Good job, everybody knows. Molten zinc chloride was electrolyzed using the apparatus shown below. Okay, choose a word from the list below which describes the positive electrode. So easy, anode. State the name of the product formed during this electrolysis at negative electrode. Negative electrode meaning cathode. So this is what? Molten zinc chloride, right? Zinc chloride. So negative, what will go towards negative? The positively charged cation, right? So zinc will be deposited at the negative electrode, and positive electrode chlorine. Now zinc is a metal, so solid metal. Positive electrode chlorine gas, yellowish green gas. Suggest the name of a non-metal which can be used for the electrodes in this electrolysis. Good job, Ajwa. Carbon in which form? Yes, graphite. Yes, graphite. Good job, Ajwa. Good job. Yes, graphite. So this wasn't that difficult. It was looking very long, but it was easy. Okay, that's it. We will try to finish. Okay, inshallah, we didn't get a chance to do past papers. Okay, inshallah. Can we do one more? No, Hala. Yeah, I have to go because this meeting room is required. Okay, so inshallah, tomorrow, inshallah, from 8 to 9, same, our old time, and we will do biology tomorrow. Okay, transport in animals. We will do inshallah blood vessels and immunity. Just okay, jazakallahu khairan. You have a question? Will we do revision? Yes, inshallah, inshallah. It was helpful and enjoyable. I could not take your questions today. You have a question, Nabil? Okay, ask. Oh, you want me to do one more question? No, I'm so sorry. We're already 10 minutes late. Okay then. Assalamu alaikum. Assalamu alaikum.
Walaikum assalam.
Yes, Hala. Biology tomorrow.
Okay,
Inshallah.
bye.
Okay, assalamu alaikum.
I have one question.